Current is flowing through a conducting hollow pipe whose area of cross section is shown in figure. The value of magnetic induction will be 0 at. Options are given. In the question, there are 3 points P, Q, R. So we have to find out the magnetic field at P, Q and R. By Ampere's circular law, closed integral B dot dl is equal to mu 0 I. That is, magnetic field over a closed path is equal to mu 0 times current enclosed by the path. Suppose there are current I1 and I2 inside the closed path, then the total current we can write it as I1 plus I2. So magnetic field will be according to this current. So if we consider the point P, in this area there is no current, so there is no magnetic induction at P. At P, magnetic induction is equal to 0. Whereas when we consider Q and R, see, in this region, inside this region, both current is there because current is flowing through this area. So when we consider Q and R, there is current. So we can say at Q and R, magnetic field not equal to 0. So correct option is option D. At P, magnetic induction B is 0 and not 0 at Q and R. Option D is the correct one. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its cross section. The ratio of magnetic fields at A by 2 and 2A is. Options are given. Here long straight wire is given and its radius is given as A, and we have to find out the ratio of magnetic fields at A by 2. So this point A by 2 comes inside and 2A that comes outside. So equation for magnetic field inside is mu 0 I R divided by 2 pi R square. So it is mu 0 I R is A by 2 divided by 2 pi into radius is A, 2 pi A square. And again B outside. That is equation is mu 0 I by 2 pi R, that is mu 0 I divided by 2 pi into 2A. So when we take the ratio B A by 2 divided by B 2A, that means B inside by B outside. B in by B out. Okay, you will get 1. So the correct option is option C. Consider 6 wires into or out of the page, all with the same current. Rank the line integral of the magnetic field from most positive to negative taken counterclockwise around each loop shown. We can apply Fleming's right-hand rule for magnetic field and current. You can check with your right hand. If the fingers represent direction of magnetic field, thumb represent direction of current. If the magnetic field is in the counterclockwise direction, then current is coming out of the field. That means thumb is out. If the magnetic field is clockwise direction, that means current is going into the field. So here it is said that magnetic field it is counterclockwise. So first we should consider this one. Here 4 loops are given A, B, C, D. Let us consider the first one A. We can apply Ampere's circuit law for all the loops. That is Ampere circuit law is closed integral B dot dl equal to mu 0 into I. Here for the first loop, 3 currents are going out. 3 current out minus 3 current in. So you will get 0. For the second loop, again mu 0 into 2 currents going out, 1 current going in. So you will get mu 0 into I. For the third loop, mu 0 into, for the third loop C, 1 current is going out, 2 currents going in. So you will get minus mu 0 into I. And for the last loop D, again we will get mu 0 into, no current is going out, 1 current is going in. So you will get minus mu 0 into I. So if you check all the options, you will see that both C and D are minus mu 0 I. And which is the biggest one? B. For the loop B, it is mu 0 I. That is the biggest one. And next one is A. And next one is C and D. So option C is the correct one. There are 50 turns of a wire in every centimeter length of a long solenoid. If 4 ampere current is flowing in the solenoid, the approximate value of magnetic field along its axis at an internal point and at one end will be respectively. Options are given. So we have to find out the magnetic field inside the solenoid and also at the one end of the solenoid. Equation for magnetic field inside a solenoid is mu 0 Ni, where N is the number of turns per unit length. Here N is given as 50 per in every centimeter, means in centimeter. When we convert into meter, we will get 50 divided by 10 raised to minus 2 or 5000. So we can substitute this, that is 4 pi into 10 raised to mu 0 is 4 pi into 10 raised to minus 7 into N is 5000 into I is given as 4 ampere. So you will get 25.1 into 10 raised to minus 3 Weber per meter square. And at one end, it is half of B in. So let us take the half of this one. You will get 12.6 into 10 raised to minus 3. So option B is the correct one. Two parallel wires of length 9 meter, each are separated by a distance 0.15 meter. If they carry equal currents in the same direction, exerts a total force 30 into 10 raised to minus 7 Newton on each other, then the value of current must be, you should find out the value of current. We know that when there are two parallel conducting wires separated by a distance r, then the force per unit length between them is mu 0 I1 I2 divided by 2 pi r. Here both the currents are same, I only, and the direction is same, direction of currents. So there will be a force of attraction between them. Here F is given as 30 into 10 raised to minus 7 Newton divided by length 9 meter equal to mu 0 is 4 pi into 10 raised to minus 7. I1 and I2 are same, so it is I into I square divided by 2 pi into R is 0.15 meter. So we can find out I from this equation. When you calculate this, you will get 0.5 ampere. So option D is the correct one. If an electron is moving with velocity v in an orbit of radius r in a hydrogen atom, then the equivalent magnetic moment will be. Equation for magnetic moment is I into A. where I is the current, A is the area. Suppose the electron is moving in this orbit, then it will constitute a current. Then if A is the area of this orbit, then magnetic moment will be perpendicular to this plane. Then equation for magnetic moment is I into A. Current is charge divided by time, that is rate of flow of charge into area. We can write E. For electron charge we write it as E. Time we can write 1 by frequency, and area is pi r square. So we can rearrange the equation. F will go to the numerator, EF into pi r square. Again we know that omega equal to 2 pi f. Angular velocity equal to 2 pi into frequency. So frequency we can write omega by 2 pi. Also linear velocity v equal to r omega, or we can write omega equal to v by r. We can substitute this value in this equation, so you will get f is equal to v by r into 2 pi is there. So let us substitute the value of frequency in this equation. So you will get E into v divided by r into 2 pi into pi r square. So you will get E v r divided by 2. So the correct option is option D, EVR divided by 2. A 5 centimeter, 12 centimeter coil with a number of turns 600 is placed in a magnetic field of strength 0.1 Tesla. Maximum magnetic torque acting on it when a current of 10 raised to minus 5 ampere is passed through it will be. We are going to find out the maximum torque. Equation for torque is M cross B, where M is the magnetic moment, B is the magnetic field strength, or we can write MB sine theta. When theta equal to 90 degree, we know that sine theta is 1. So torque will be maximum. That is MB into 1. So MB. If there are n number of turns, then torque will be n into MB. N times torque. So we can write n into magnetic moment, we can write it as I into A into B. So let us substitute. N is 600, I is 10 raised to minus 5, A is 5 centimeter, that is minus 2 10 raised to minus 2 into 12 into 10 raised to minus 2 into B is 0.1. So when you calculate this one, you will get 3.6 into 10 raised to minus 6 Newton meter. So option A is the correct one. Two galvanometers A and B requires 3 milliampere and 5 milliampere respectively to produce the same deflection of 10 divisions. Then options are given. A is more sensitive than B, B is more sensitive than A and B are equally sensitive. Sensitiveness of B is 5 by 3 times that of A. Let us check it. Galvanometer sensitivity, current sensitivity, we can write it as 5 by I, where phi is the deflection, I is the current. So we can write phi is equal to sensitivity into current. Here phi 1 equal to S1 I1 and phi 2 equal to S2 into I2. Here deflections are same, that means phi 1 equal to phi 2, or we can write S1 I1 equal to S2 I2. S1 into I1 is 3, S2 into I2 is 5. So S1 is 5, 3 will go to the other side, 5 by 3 S2. That means 1.6 S2. That is S1 is 1.6 times greater than that of S2. That means A is more sensitive. Sensitivity of A is more. So option A is the correct one. A is more sensitive than B. The coil of a galvanometer consists of 100 turns, effective area 1 square centimeter, the restoring couple 10 raised to minus 8. The magnetic field between pole pieces is 5 Tesla. The current sensitivity of galvanometer will be. Options are given. Current sensitivity is 5 by I, that is deflection per current. That also we can write NBA divided by C, where C is the couple, N is the number of coil, B is the magnetic field, A is the area. Here N is given 100, B is 5 Tesla, A is given as 1 square centimeter. So when we convert it into meter, 10 raised to minus 2 whole square divided by C is the couple, that is 10 raised to minus 8. Let us calculate this one. So we will get 100 into 5 into, this is 10 raised to minus 4 divided by 10 raised to minus 8. When we calculate, we will get 5 divided by 10 raised to minus 6, or we can write it as 5 radian per 10 raised to minus 6 is micro ampere. So answer is 5 radian per micro ampere. Option D is the correct one.